that I consider is the following. So to find domain omega in the plane, so this one here, whose boundary consists of the real axis, which I denote by B, and a curve which is assumed to be periodic and denoted by S. And in this domain one has to find a function psi which satisfies minus the Laplace of psi equals gamma, a constant. The function satisfies constant Dirichlet boundary conditions, so both on the free boundary, where it is assumed to be 0, and on the fixed boundary, where it takes some other constant value, which I will denote it by minus m, and in addition on this curve S, it also has to satisfy a nonlinear boundary condition, gradient psi square plus 2gy equals q. So we are working in the plane, and the coordinates are x and y. The period of this wave is L. So G is a given constant, gravitational constant, and so gamma is also a constant, and Q is also a constant, but and Q and M will be parameters. So in fluid dynamics, this would correspond to a steady water wave. So the domain omega will be the domain occupied by the water, and so which is above a fixed horizontal bottom, and here above the curve, so there is an air region. Psi is what is called the stream function, which gives rise to a stationary velocity field uv equals psi y minus psi x. Water is assumed to be incompressible, so that's why it can be described in this way. The only force acting on the fluid is gravity, which leads to this term in the equation, and this nonlinear boundary condition, so it's called Bernoulli condition. So it comes from the requirement that the pressure at the surface of the fluid has to be in equilibrium with the constant atmospheric pressure in the air above. And so this is well, can be regarded either as a stationary problem, so there is no time dependence, although so water moves, so with velocity field depending on space but not on time, but also as a traveling wave, so in which the this shape moves at constant speed. And the equations that I wrote are valid in the moving frame. So this is a particular case of the problem of waves with general vorticity, in which in the right hand side of this equation, so we would have possibly arbitrary function of psi. So the vorticity of this wave is minus delta psi, and so from fluid dynamics considerations, so it must have the same level sets as psi, and so delta psi is a function of psi. So however, so during this talk I will consider this the case when gamma is a constant, possibly non-zero. Although the case of general function is also of well, even greater interest, so to say. Okay, so and so this is a free boundary problem in which the curve the boundary of the water domain has to be determined as part of the solution of the problem, and all the solutions that I will be discussing here are smooth. So everything holds in the classical sense. Okay, and I am interested in existence of solutions to this problem, and I'm going to be using a complex and harmonic analysis approach to construct such solutions. So the goal is to provide an existence theory for waves of a large amplitude using bifurcation theory. But in order to do that, I will reformulate this free boundary problem in an equivalent way. And the equation that I get is this one, which is written here. So to get to this, I'm going to be using some complex and harmonic analysis, so to say. So let me explain to you briefly, so what are the objects occurring in this equation. So the main unknown is this function v that you see occurring in a lot of places, so which is a 2 pi periodic functions of one variable. So the free boundary problem has been reduced to, the unknown is just a function of one variable. So there is also this operator ckh, so which is some sort of version of the Hilbert transform, but rather than being associated in the usual way to a disk or to a half plane, so it is associated either to an annulus, so it can be regarded as relating the real and imaginary parts of holomorphic functions in an annulus or in a strip with periodic boundary conditions. So I will make everything clearer later on, and it depends on two parameters. So in the form kh, so where k is related to the period, so that L is 2 pi over k. So this k is called the wave number, and h is some sort of mean depth of this domain, but it's not exactly the average depth, but something called conformal mean depth that I will also describe. And you see all these other constants that I had in the equation, so gravitational constant, so this Bernoulli constant Q, the flux M, and these square brackets throughout the talk will denote the averages of periodic functions. So, so there are two equations, but this is an equality of functions. So this Hilbert transform maps functions of one variable to functions of one variable. I will give the precise definition. So this function has to be identically zero, while there is also an equality of numbers as a second equation. Yes, so so I want to explain how these equations arise, and then how can I use them. Well, so all of this comes from this. So these equations encode everything, and basically this function little v has so nothing to do with the velocity, but the so v will be the vertical coordinate of a parametrization of the free surface. So v of x in R. So v is the vertical coordinate, while the horizontal coordinate is x over k plus the Hilbert transform of v minus h. So so v describe the wave elevation in a suitable parametrization of the free boundary using conformal mappings. Okay. And So the advantage of this formulation is that it can describe waves of arbitrary geometry. So no matter how complicated the overhanging and so on, and also makes no assumption on the level set of this function psi inside the domain. So the aim is somehow to see whether we can prove the existence of waves with overhanging shapes, or at least maybe the shape can be a graph, but the level sets are not graphs. So there are, because okay, so typically, I mean, the simplest situation is when this is a graph and every level set is also a graph. But so here a critical layer is a level set which is closed somehow. So in the case when there is no vorticity, so it has been proved with Spielvogel and with some refinements that so even if you start at the beginning with arbitrary geometry, so such things cannot occur. So the wave is always a graph. But on the other hand, so if this constant in the right-hand side of the equation is non-zero, so there have been numerical computations from a long time ago, which people have computed this wave with mushroom shape. So it was, yeah, our aim was to have an approach which could somehow capture this kind of waves. So, which we only managed to do partially. And so, okay, so these are very classical problems. Going back a long time ago. Okay, so for existence theory in this kind of waves, so especially in the case when gamma is 0, so which is called the irrotational case, but also for waves with the general vorticity, so the approach is always to reformulate the problem over a fixed domain, and then use nonlinear functional analysis, bifurcation theory to construct solutions. And so I will mention some possible approaches that have been used in the past. Okay, so some of this I won't say anything at all. So Nekrasov quite messy, and then so this is Babenko formulation for waves of with zero vorticity and of infinite depth, in which this is the usual Hilbert transform. So my equation is a generalization of this one actually, but with a lot more terms due to, so this is for zero vorticity and infinite depth. And there is also something involving the Dirichlet-Neumann operator, but again valid only for zero vorticity. And for general vorticity, so there are two possibilities that have been used so far of transforming the problem to one in a fixed domain. So one is to use this hodograph transformation due to Dubray-Jacotin. So because psi is constant on top and bottom, so it can be used as a coordinate while we keep the first coordinate as x. So xy goes to x and psi. But this is valid only if psi is monotone. So psi y either always greater than 0 or always smaller than 0. Yes, so this makes sense for any semilinear equation, but one has to have a condition like this. So which yeah, so it's I wanted to treat these critical layers and the overhanging waves in which necessarily psi y is 0 somewhere, and there is also some other flattening transformation in which if the curve has the form x eta of x, then the transformation is x y over eta of x. So it's like you project this over the, well, and then the new domain is also a strip, but this also requires the domain to be a graph. So yeah, so the formulation that I am using seems to be the only one I know, or people working in this area know, that can handle arbitrary geometric shapes of the free boundary. Unfortunately, it is restricted to constant vorticity and still based on complex analysis. So it's interesting open problem. So if you have a semilinear equation in general, how you transform this to problem to one in a fixed domain. Okay. So and the approach was to that we use was to regard the fluid domain as the conformal image of a strip. Yes, so one is looking for a conformal mapping U plus IV, which would map a strip into this region. So now such conformal mapping exists for any domain bounded by a curve in the plane, and also this periodicity requirement here translates into some periodicity of this conformal mapping, in which we can say that maybe one box in this strip will be mapped into one period of the wave, at least if some symmetry is assumed. Okay, so but we have some freedom in choosing this strip, because we can always make a dilation, and we still get a new conformal mapping. So in order to normalize things, what we do is to choose this the horizontal length of this box to be equal to one period of the wave. Yes, and then so what about the vertical dimension? So this will be a number called h, which is my definition of conformal mean depth, and it is some sort of a geometric invariant of a periodic domain. So the situation is similar to the one encountered in conformal mappings of doubly connected domains. So if there is a region like this, then so there is a conformal mapping between this and then annulus. Yes. So this can always be dilated, but if we choose this outer radius to be 1, then there is a unique value for the inner radius, which is called the conformal modulus. So which cannot, yes, so such conformal mapping is possible only for one value of this radius. So something similar happens here. If I choose the horizontal period of this box to be the same as the period of the wave, there is a unique value for the vertical coordinate, which is this conformal mean depth. But I would rather work with on a box of horizontal size 2 pi, and so I do a dilation. So this L was equal to 2 pi over k. So if I want to make this 2 pi, then this vertical dimension would be kh, and this is why I have this product kh occurring in the equation. Okay, so finding the domain is the same as finding the conformal map, and the conformal map is uniquely determined by its restriction to the real axis, which I call little v, so which is a function of one variable. Because if I know this little v, then capital V is solved is obtained by solving the Laplace equation with boundary values little v, and with values on the bottom of the strip to be 0, because this line is supposed to be mapped into the real axis. So little v determines capital V by solving this Laplace equation, and then capital U is determined by taking the harmonic conjugate of capital V, and so knowing little v enables us to determine the conformal mapping. This is true for any domain without taking into account any PDE or anything. So, and because I want to find some special domains in which this PDE is solvable, this will lead to some special properties of this function little v, which I'm going to describe, and lead to the equation that I presented at the beginning. So, okay, but first of all, the definition of this Hilbert transform. So, so if we take a strip between the lines y equals 0 and some other line, and we start with a function of one variable and 0 mean, then we solve the Laplace equation with boundary values little w and 0 on the bottom, and find the harmonic function w, and then take another harmonic function z, so that this is holomorphic in the strip, which is periodic, and the Hilbert transform of w associated to this strip of height d is the restriction to the real axis of this z. Yeah, so start with the function of one variable, extend harmonically with 0 on the bottom, take harmonic conjugate, take the restriction to the top, and that gives the Hilbert transform. So similar way like in the disk or in the annulus. Yeah, so this is a linear operator, and so it is enough to give its action on the trigonometric system. And then you can use separation of variables and get this so it maps cosine into sine with some multipliers and so on. And it also has so this is my definition, and extended by linearity to L2. Okay, so in the case of, and it also can be represented as a convolution, but so for d equal infinity we get the usual Hilbert transform convolution with cotangent over 2, but this is a new operator. Okay, and because of the Cauchy-Riemann equation, so this Hilbert transform is related to Dirichlet-Neumann operator. Namely, so Dirichlet-Neumann operator for this function w would mean taking the y derivative of this capital W. So start with Dirichlet data, solve Laplace, and take Neumann. So it's wy, and because of the Cauchy-Riemann, so the Dirichlet-Neumann is the Hilbert transform of the derivative plus a constant involving the average of the function. So so this is the definition of the operators involved in the equation. So how do I get those equations that I started there? So the equation was delta psi equals minus gamma, but so if we add this quadratic function, we get harmonic function because the Laplace of this is gamma. And the harmonic functions are invariant under conformal mapping. So if I compose this thing with u and v, so you get something like this, and I add a constant, I get also a harmonic function. So the original, so if I have a solution of this equation, I compose it with the conformal mapping, and somehow I get some harmonic function zeta in the strip. So harmonic 0 on the bottom. It has this kind of Dirichlet boundary conditions on the top. And this comes from the Bernoulli condition if one does the change of variables with the chain rule and so on. So, And now we're using the Dirichlet-Neumann operator. The fact that we have a solution of this problem can be written equivalently in this way. So, so let's see. So q minus 2gv is here, and then vx is v prime. So vy is the Dirichlet-Neumann operator of associated to v. So it's the Hilbert transform of the derivative plus constant related to the average. And then this zeta y is the Dirichlet-Neumann operator associated to this function, so which involves the average plus Cauchy-Riemann equation. So Hilbert transform of the derivative and so on, and this vy. So v is here and vy is the. So we have just transformed the equation by this conformal mapping. And so this is the new equation, so which is not what I wrote at the beginning, but so we have in this quite simple way, we have reduced everything, the problem to this equation of function of one variable, and moreover this function v has the average equal to h. So okay, so this is a bit maybe not technical, but and so this is the first theorem that we proved 3 years ago. So it's easy, as you can see. So if there is a periodic wave, then there is a constant, the conformal mean depth, and the function with average h, which satisfies this. And then the curve is the image of the real axis through this conformal mapping. So it has so the free boundary has this parametric representation, and you can go in the other direction as well. So if you start with the solution of this equation, then you construct this curve, but which need not always be injective. But if you assume that it is injective and in the upper half plane, then in the domain between the axis and this curve, you can solve the problem and you have a solution. So this is the first thing, and maybe I could have stopped here and study this equation. Yes, please.
In the slide before this.
Yeah.
So where is the overdeterminate condition coming from the free boundary?
Yeah.
It's translated to just boundary condition?
Two boundary conditions. So this zeta, which is essentially obtained by composition with the conformal mapping, so satisfies both Dirichlet, which comes from Dirichlet here, but I have added this v square and so on, so it is this. And the other one is comes from Bernoulli. Okay. So it is an overdetermined problem in a strip.
Okay.
And I can, yeah, so, and it involves the Dirichlet data of a function and also the Neumann derivative. So this is zeta y is the Dirichlet-Neumann operator applied to this function. So that's the basic idea.
Then what is the free parameter here?
So I have kept the same constants as before. So m and q will have to be determined as part of the solution. So a solution of the original problem exists if only if this exists. Yeah.
Also, the mapping itself is free.
Yeah. So it is the mapping that has to be determined, and it is the restriction to the real axis, which is the key thing. And in order for this to lead to a solution of the problem, one has to satisfy exactly this. Okay, so this formulation is enough to do local bifurcation theory, so to construct small amplitude solutions of the problem. But in order to do global bifurcation, so one has to check some compactness assumptions on operators which are not clear at all from this formulation. So which means that now I start from this and reformulate it in an equivalent way using something called Riemann-Hilbert theory, which is something a bit technical, and I won't have time to get into details. So, but I'll just give a brief idea. So the previous equation can be equivalently written as this, the equation that I claimed at the beginning. The second equation is just the average of the equation I had before, so follows immediately. And so let me explain a little bit the connection between this and that. So recall the equation satisfied by this zeta. So harmonic 0 and with this boundary data, and the Bernoulli condition was the fact that this expression here is 0. Yeah, but okay, so now ignore the fact whether it's 0 or not. So you can just write this by some algebra in this form. So if the original equation holds, then this thing is 0. So this expression here being 0, and this expression here being the boundary data of an analytic function, so I get that this thing here up to here, so stopping here, is the boundary data of an analytic function. But Vy plus Ivx itself is analytic, so I divide by this, so I get this, and then instead of the sum of square I get this. So this is equivalent to the fact that this is the boundary data of an analytic function, but then the real and imaginary part are related by the Hilbert transform. So if I write down the real and I get exactly the equation as before. It's not really a big deal, and it's not so important. So okay, so I have obtained this equation here, and now I would like to study existence of solutions using the bifurcation theory. Okay, so this has a variational structure being the critical points of an energy, but okay, so let me skip this. Okay, so first of all, this problem has trivial solutions in which the free surface is flat. So y is 0, y is h, and psi equals psi of y, and so in this case the equation becomes psi y equals minus gamma. And so if we solve this and impose all these boundary conditions and so on, so psi equals 0, psi equal minus m. Yeah, so this problem can be solved uniquely and leads to a quadratic function, and the corresponding q in the Bernoulli problem has this expression. So the problem has a one parameter family of trivial solutions with a flat profile, and if I am to represent the solution set in some function space, so if I put here m and here q, and then a space x for this function w, so in this horizontal plane, so there is a parabola of trivial solutions. So there is a curve of trivial solutions K3. And the first question is, so which of these can be perturbed to lead to waves of small amplitude, so which are almost flat, and then how these families of small waves can be extended to waves of large amplitude, possibly overhanging. So Yes. So first of all, let me mention the abstract result that we are going to use. So, so this is related to somehow to the Rabinovitz, the Crandall-Rabinovitz local bifurcation theorem, and to the Rabinovitz global bifurcation theorem. But it exploits the additional structure that the operators are real analytic. And in this form, so the result is due to Dancer in 73 and with some refinements by Buffoni and Toland. So the abstract setting is this. So we want to solve a problem f of lambda u equals 0, where lambda is a parameter and u belongs to a Banach space, and f is from R cross x to y, or only in an open set. And the problem has a line of trivial solutions. So this is lambda, and this is x. Okay, then so suppose that at this point lambda star, the assumptions of the Crandall-Rabinovitz theorem are satisfied. So the kernel of the linearization with respect to u is one-dimensional, the range has a codimension 1, and the transversality holds. So this in itself gives the existence of a local curve passing through lambda star. So this is very, very standard, but what is not so well known is that this curve can be extended globally in both directions if the following compactness assumptions are satisfied. The linearization with respect to u is Fredholm of index 0 along solutions, and bounded closed sets of solutions are compact. And then so if these assumptions are satisfied, then this Dancer's theorem tells us that so there exists an extension of this local curve, which with some, it's real analytic, and so to say, so which either it is a closed loop, so it returns to the same point, or goes to infinity in the function space, or approaches the boundary of the domain where the operator is defined. So so this means that so this Qj is a sequence of sort of compact sets exhausting the open set. So the solution curve eventually leaves every compact, so either approaches the boundary or goes to infinity. And so this is the abstract result, which applies to my equation involving that function w, and the result we obtain is the following. So there was this one parameter family of trivial solutions. Then along this curve we are able to identify points m1, m2, m3, and so on, m-1, m-2, and so on, so that from each of these there is a bifurcation of a curve of non-trivial solutions. So we know the asymptotics and so on. And yes, so these curves either go to infinity or sort of approaches the boundary of the domain in function space where the operator is defined, or it is a loop. Yeah, so we are just applying the abstract result. So either it is a loop or it goes to infinity. So it is this condition that mqv along the curve, so 1 over this going to 0 is the same as this thing going to infinity. Our approach is the boundary of the open set. So the open set being essentially the set where so the set O is MQV with Q minus 2GV greater than 0. So which in the original in the physical plane, so this would correspond to the waves approaching 1 with a stagnation point. So we had gradient square was Q minus 2GY. Yeah, so the solutions are not just the local perturbation or something trivial. So there are, we did prove existence of solutions of large amplitude. So either with the norm going to infinity, or approaching singular waves where this expression is 0. Okay, and briefly, so how these compactness assumptions in the previous theorem are obtained. But okay, so first of all, yes, so some of these waves do have critical layers. So even in even those of small amplitude that are perturbations of trivial flows, so the level sets look like this. So it is this kind of solutions that couldn't be obtained by any other approach, which we do obtain. But overhanging waves, so it is open problem yet. Okay, so now the equation itself looked quite messy. So let me write it once again and explain the relevant structure that is involved. So we just rearrange it in this way using algebra. Just algebra, and then we look at the most singular terms. So this Hilbert transform is operator of order 0, so to say, preserves smoothness. So maps Hölder functions into themselves and LP functions into themselves, and so on. So the most singular terms are those involving derivatives. Yeah, so this and this and this and okay. But apart from this one in the left hand side, all the others occur in these special combinations, you see, so like commutators. So what notation should I use? KH of FG minus F CKH of G. So these are so they are terms of this form, commutators. And the nice thing about this is that they are smoother than one we would expect at first sight. So if the original function is Cn with Cn alpha, so n derivative is Hölder of exponent alpha, and this is just periodicity, then each of these two terms loses one derivative. So because it involves one derivative, but the difference of them so is smoother. So it only loses a little bit in the exponent. Yes. So the difference is smoother than the individual terms. And it is this thing which is the most important in the analysis, and especially so you see that all of these terms are multiplied by the vorticities. So the presence of this constant gamma in the equation, as opposed to gamma equals 0, introduces only these commutators, which are lower order terms, are smoother than one would expect. Okay, so the right hand side is smoother than one would expect, and then we divide by this Q minus 2GV, assuming that it is greater than 0. And then essentially I would like to invert this, but for that, so you add V in order to invert it. But in any case, so if we do this, so we manage to write the equation as a fixed point as of a nonlinear compact operator. This is the so it is the presence of these commutators which enable us to write it as a fixed point of a nonlinear compact operator, which was not possible to do from the very first formulation I obtained. So in that setting, these compactness properties were not obvious at all. And so being a fixed point of a compact operator, this enables applicability of this abstract theorem of Dancer, Buffoni, and Toland. And also this smoothing effect of the commutators enables us to use a bootstrap argument to show that any solution with any limited regularity is C infinity, because there is this lack of balance of smoothness. Yes, so the right hand side is has one derivative more than the left hand side, so you bootstrap and get C infinity. Okay, so what about this the properties of the waves that we obtain? So so they give rise to solutions only if this wave profile is injective and remains in the upper half plane. And along the solution curve, at the very beginning, so for S small, we observe that so this function is positive and monotone, and the real part is contained between these numbers. And we asked ourselves to what extent these properties remain preserved along the solution curve. And for that, so we consider the maximal set along which they are preserved, and then either it is this remain true up to infinity, or there is a point at which at least one of them fails, but we prove exactly that the one which fails is equality here. So what does this mean in geometric terms? So yes, and the solutions that we consider are always symmetric. So V is even. So in half a period, V always decreases. It does something like this. So the vertical coordinate moves downwards. But about the horizontal coordinate, so there is no information, so it could move both to the right and to the left, and so this is just half a period of the wave. And as long as this monotone curve does not touch these two vertical lines, when we extend it by symmetry and periodicity, it remains injective. So this is a very good property. But so the only bad thing that can happen is if some of this touches the axis somehow, and then when you look at the reflection, so it also touches the axis at the same point, and so this is no longer injective. And in principle, this could happen also on this line here. But this we can rule out. So something like this is not possible, but something like this is possible. So either the solutions are physical for all the values of the parameter up to infinity, or they are physical until there exists a limiting configuration where this relation is true, which means exactly what I have drawn here, that there is touching above the so-called trough line. So yes, so we have
So this is the C bottom here, and it touches, that's
no. The bottom is here, and is never touched. So it's just the surface touching itself, like bending on itself, just like in this picture. So if you imagine that it extends by symmetry, it touches at such a point. Okay, so we have obtained therefore existence of these solutions just by, of large amplitude by applying the abstract result, but that only uses very general assumptions. Very basic structural properties of the equation. So the qualitative properties of these solutions remain still to be investigated. So, for example, there was this possibility that the solution curve goes to infinity in function space, but we believe that that does not happen. So, would like to prove that the curve of solution does remain bounded, and but instead it reaches the boundary of the open set. So there will be a limiting configuration where this is 0. So this would correspond to a stagnation point at the top of the wave, and in that case, yes. So I have worked on this, and so it is. Then here there will be a corner of 120 degrees. So this limiting configuration either is has a singularity at the crest, so possibly either being a graph or overhanging, but actually don't know whether the solutions are overhanging. So limiting configuration will be either this, or maybe this one, which remains smooth but touches itself on the on this line above the lowest point. Yes, if you extend by symmetry, it will touch. And the fact that this, all of these three possibilities, it seems that they are possible. So this is what the numerics suggest, but they remain open problem. And so with this I finish. So thank you, and happy birthday, Nicola.
What do you assume a priori in the free boundary?
That it is a smooth curve like C1 alpha, periodic in the horizontal direction, and that's all. So no, and the injective. So no restriction on the geometry. So it could be really wiggly, but it always can be parameterized conformally. I mean, that's the idea. I can describe arbitrary geometry with this conformal mapping.
In this commutation estimates, you get the derivative of the free boundary, right?
Yeah, so it's related to smoothness of the, yes, I mean, and the conclusion is this solution. So even if you start with C1, so they are C infinity, although, by some other method, I mean, they are real analytic, in fact. So I think the standard free boundary, but C infinity you get it from commutator. And it is important that in order to, so this Q minus 2GV greater than 0, so I mean formally in the Bernoulli condition, the gradient being different from 0, yes, so this smoothness is connected to the fact of gradient being non-zero, the points where it is 0 being those that I described in my earlier talks. But yeah, so this is the smooth case. And singular solutions, you obtain them only in the limit somehow. So when the solution curve reaches the boundary of the domain where the operators are compact and so on.
So your gamma can be both positive and negative, right? So what's
Yeah.
the effect of the sign is due. So
Yes, so in this theory, I mean, so all that I said is valid for any gamma, but depending on the sign of, well, so the presence of absence of this kind of critical layer, so it is this which is related to the sign of gamma. So in one situation, so if the sign of gamma is the same as the sign of something else, so these are not possible. So it is, yeah, and in the so it is both the sign and the signs of gamma which determines which kind of this behavior could happen. So, but everything is numerics about this.
Okay. Well, thank you again.